In section 8.3, we're going to work with some inverse trig functions. And one of our goals is to kind of analyze these graphs for arcsine, arccosine, and arctangent and find some exact values. So something that you hopefully watched before watching this video is brushing up on some inverse functions from college algebra. Remember that we do want inverses to be restricted to where they are functions, and so they pass the vertical line test. For them to be one-to-one, they also have to pass the horizontal line test. It is important to recognize that in trigonometry, inverses operate slightly differently. We do have to restrict their domain because otherwise they would not be functions. They would all fail the all fail the vertical line test. I'm going to show that to you on the next page. In this figure right here, you're going to see you have the tangent curve and you see this dashed red line that is crossing at the same spot on every single tangent curve. So you're going to notice that it's failing the horizontal line test an infinite number of times, okay? There's a million different values for where tangent of x is equal to -1. So ultimately, we have to restrict the domain in order to be able to accurately say, yes, this is where tangent of x is equal to -1. What's going to happen is you're going to restrict it here, and I'm going to tell you why in just a little bit, okay? For now, just know that there will be a restriction. Okay. There are three requirements for restricting a trig function. It has to have all the quartile one angles. So all quartile one angles must be included. Okay. The second thing that we need to keep in mind is that it has all of the range on the domain because we're inverting. Okay. It achieves the entire range on the domain. And the last thing is that it's as continuous as possible, which means no gaps, right? We can't have any jumps, any gaps, no skipping anything, no asymptotes. So um, in this case, for tangent, if we needed to select a standard solution, we would look at the section in blue. The reason we look at the section in blue is because in yellow, here is all of your quartile one angles. Okay. Notice that it also has your entire range from bottom to top. Okay. And from left to right. Okay. From left to right. It has everything we need. And then in terms of continuousness, the asymptotes are right here. And so we are not skipping over anything. We're getting everything from the left all the way to the right. Okay, there is no jumping over anything. So we would end up choosing this section. And so here for our point, this is where we would say tangent of x is equal to -1. Okay, this is where we would say. Okay, so that's going to be negative pi over 4. And that would be what we say is the answer for that. Now I'm going to show you what all of these curves are going to look like when they are turned essentially and made inverses. I'm going to do my best to make sure that every piece is explained. So here's the sine curve. Okay, we know that the sine curve is going to continue forever, right? In this version, it is continuous. Okay, and it passes the vertical line test, right? If I just draw a vertical line, it's only ever going to touch that thing once. Okay, it currently does not pass the horizontal line test. And that's going to be a problem for us. Okay. So based on the three rules, which section do we want? Okay. Well, let's look at the three rules. We want everything from quadrant one. So that immediately tells me I need this section at the very least. Okay. So that's going to be in blue. From 0 to pi over 2, that's going to be quadrant one. And I need my full range. Okay. I need my full range without failing the vertical line test. Okay, my full range without failing the vertical line test. If I go this way, I fail. Okay, so I'm going to go this way because in this scenario, I go from -1 to +1. Okay, and I have my entire range. So that'll be -1 to 1. That works. And so this is the snippet that we are zooming in on right here. Okay. Zooming in on that, our restricted domain is from negative pi over 2 to positive pi over 2. Something that is important to note is yes, this is a negative pi over 2, which means we are moving clockwise, okay, which is not something we usually do. And then we're going to go this way for counterclockwise, okay? So we have negative pi over 2 all the way to positive pi over 2. And that's going to be your restricted domain for the inverse sine function, okay? Now look, what would happen if we were to continue when you graph this further, right, is that it would immediately fail the vertical line test. Like if that curve were to continue oscillating, it would fail at every single spot. Okay. And so that's why we have to restrict it. Now remember, I'm going to remove this so I have a little bit more space. Remember that for coordinates, those coordinates simply just flip-flop. So X and Y are just going to switch. So over here on my regular sine curve, okay, I have a point at 0, 0, and then I have a point at pi over 6 and 1/2, okay, and both that works for both the positive and the negative. The same for pi over 4 and 1 over root 2, okay, and then the same for pi over 3 and root 3 over 2, okay. Now, when those switch, I have the same values, but x becomes y and y becomes x. So now at plus or minus 1/2, I am at a height or depth of pi over 6. At a distance of 1 over root 2, I'm at a height or depth of pi over 4. At a distance of root 3 over 2, I'm at a height or depth of pi over 3. Okay, so those points are just going to flip-flop. Okay. On the bottom, you'll see this little note right here. It means that x is equal to sine y between negative pi over 2 up to pi over 2, including pi over 2. Okay, there is no asymptote or anything, so we can include the pi over 2. What we're going to see later is with tangent that there are asymptotes, so we do become limited at our ends. Let's look at cosine. It's going to look really similar. We want our full range. So our full range is going to be from 0 to pi, okay? Because if we go backwards, we fail. Okay, we're going to fail the test. We also want to have our quadrant 1, so we know for sure we're going to be including this section. This is your quadrant 1. So zooming in, we end up with um, this graph, okay? If you were to plot it, we want this to be our restricted domain. Similar to before, if we want to write our x and y values, okay, we would have 0, 1, pi over 6, and root 3 over 2, pi over 4, and 1 over root 2, and pi over 3 and 1/2. And when we flip it around, you can see all of those values. Okay. So now we have a positive and a negative. So I'm just going to do the positive ones like I had here. So I have 1, 0. I have root 3 over 2 comma pi over 6. I have 1 over root 2 or root 2 over 2 and pi over 4. And I have 1/2 and pi over 3. Okay, those coordinates are just going to switch. Okay, now tangent is the one that looks slightly different because it has asymptotes. Okay? Now, right out the gate, one of the issues that we were going to face is we need the section to be continuous. It is not continuous if we were to move to the right. So by default, we immediately recognize that it makes the most sense to use the section of one full tangent, okay? Going from the left to the right, crossing at 0 in the middle. It makes the most sense because in either spot, if we were to take the left half and further left or the right half and further right, we would be cutting over an asymptote, and that's not continuous, okay? So our points here are going to be positive negative pi over 4 would yield positive negative 1 and 0, 0. Now, flip-flopping that, notice that our asymptote also becomes horizontal, and so we are limited because we can't touch pi over 2. So this is a limitation, okay? So this is going to be the parentheses for the pi over 2. That's why our domain has parentheses and not brackets. Okay? Your coordinates are just going to flip-flop. So plus minus 1 will yield plus minus pi over 4, and 0 yields 0. Okay? They can be tricky. I encourage you to use the graphs to help you visualize because just looking at the numbers can sometimes not be enough. Okay, as a reminder, they're not technically inverses of the original trig because they're not one to one, but we still use that notation. You can use sine inverse, which is that -1, or you can say arc sine. It's all the same. Okay, I have no preference. Okay, so let's do this example. Find the exact value of inverse of cosine of negative 8 pi over 3. Now we're starting to introduce these doubled up trig functions. I encourage you to start by finding the coterminal angle. The coterminal angle. So we'll start with negative 8 pi over 3, and we'll go ahead and add 2 pi k. Okay, I know that I'm going to have to add it twice, so I'm going to add negative 8 pi over 3 plus 4 pi. And I'm going to need some common denominators. So I'll go ahead and do that. That's going to get me 4 pi over 3. So now I know what I'm working with. I know that 4 pi over 3 is going to be in quadrant 3. Okay. So I know that's going to be a, oops, um, -1, negative root 3, and 2. Okay. And what I'm really interested in is the cosine of that value. Okay. So now I'm going to go ahead and find cosine from my triangle. Notice I haven't even started to work with the negative part. So according to cosine from this triangle, it is going to be -1/2. Okay. So then in part 3, I'm trying to figure out which angle is correct for that restricted domain. So which angle is correct for my restricted domain? So now I'm interested in cosine inverse of -1/2. So really what I'm asking myself is, am I in quadrant 1 or am I in quadrant 2? I know that there's two quadrants where cosine inverse exists. I do know that if cosine is negative, it has to be in the left quadrant, and that means I'm working with 2 pi over 3. Okay, so my answer is going to be 2 pi over 3. Couple steps there. Another thing that I just want to make sure you understand is that it doesn't always have to be the same number. Okay, so in all of these examples, A, B, C, and D, these are all going to work. Okay, and these are something you would plug into a calculator. So I want you to do that on your own. Okay, and what you're going to find is that these will cancel out and you will just be left with 0.73 and 7.3. But what's going to happen in D is that you are going to end up with 1.0168. These are all radian measures, okay? So make sure when you're doing this, it's in radians. Radians do not have to have pi. We are just used to seeing it with pi, but these are all radians. The reason that D is coming up different is because we are bringing it back to the restricted domain. In the restricted domain, this is going to be 1.0168. Okay. It's not going to be 7.3. 7.3 is too far outside of the domain. We have to bring it back into the domain and its equivalent angle. I just want you to keep that in mind. This isn't something that I will expect you to do on the test. Just understand that the inverses are slightly different than in college algebra. They don't just cancel. Sometimes the number can look different. Okay, here they are, graphed. Okay, I want you to see how sine would continue downward, right? And now we have flipped it. So if this point and this point would be opposite coordinates, okay? They are interchangeable, right? We do cross at 0, 0. The same thing can be said for cosine and for tangent. I just want you to see visually that it does still reflect over this y equals x line, okay? That's never going to change. It'll always reflect over that line. I think this is a really handy figure, so I went ahead and inserted it in. Your domains, your intervals, and the quadrants of the unit circle are all on there. This is something that I would expect you to learn. It would not be provided to you on this unit exam. Okay, so I encourage you to get really comfortable with that. Now let's move into solving some problems with inverse trig functions. In this case, we want to find angle theta in the triangle on the bottom right. So I'm going to go ahead and use a trig ratio to set this up. We're going to have sine of theta equals 6/10. Okay, in order to find the actual measure of theta, we need to go ahead and write this as sine inverse of 6/10 equals theta. This just goes into the calculator, okay? If we want this in radians, your calculator needs to be set to radians. That's going to give us 0.64. It keeps going, but I'll stop there. So 0.64 radians, okay? It's going to be an angle measurement since we are computing it as an inverse trig function, okay? Keep that in mind. Let's look at this next one. Determine the exact value of this expression. All you're doing is plugging this into a calculator. Okay, there is no way that you could possibly really do this without a calculator. So you're plugging it in as is, and you would get 0.94386 radians. Okay. So this is not an angle, it's outside the function, since the outside function is a normal trig function, okay? The inside would have been, but because the outside is cosine, that is a normal trig function, so this is not an angle, okay? Let's take a look at this next one. If cosine of negative x equals negative 1/3, find all possible values of x. So remember from our even and odd identities, we do know that we can essentially just ignore this and say cosine of x is equal to negative 1/3, okay? So in this case, what we can do is go ahead and draw a triangle with both of the potential triangles that make sense for this. So negative 1, 3, 3, okay? If we find this, it's going to be 2√2 or negative 2√2, okay? So if we just calculate that in the calculator, we would have cosine inverse of negative 1/3 equals x, and that would represent an angle measurement in radians. That's going to get us 1.91 radians, okay? The thing is, that's only one of the two options, okay? That's only one of the two options. Something that I'm thinking about is pi is going to be right here, and pi is approximately 3.14. So this 1.9 is this upper triangle. I also have
my lower triangle. So in order to find the value of the lower triangle, I'll go ahead and take 2 pi and subtract 1.91 radians to find my other triangle, which will be 4.37 radians. That makes sense to me because it is greater than 3.14, so it makes sense that my top triangle is 1.91, my bottom triangle is 4.37. It also asks for all possible values. So not only am I working with 1.91 and 4.37 radians, I'm also working with infinite number of loops around the unit circle for both. So plus 2 pi k, right? K is a constant, so as many times you want to go around the circle. So those would be both of your answers. Okay. If you're kind of unsure about seeing these as decimals instead of with pi, I do want you to think about drawing your coordinate plane and thinking about how at 0, it's just going to be 0. At pi over 2, that's approximately 1.7. Then we have 3.14. Then we have 4.7. And then when we get back to 2 pi, we're at approximately 6.28. Okay, we just generally use pi because it's exact versus a decimal, but sometimes we're going to be using decimals, and sometimes that means it helps to know what we're working with as an approximation. Okay? All right, our last section is just practicing working with these inverses. So your general goal is to just figure out what quadrant you're working in and then solve accordingly. I'll go ahead and draw a triangle. If I'm working with sine inverse, I know that my my tall side is my height is going to be a 1, my hypotenuse is a 2, and then I have a square root of 3. So that tells me I'm working in pi over 6. Okay, there's nothing else I need to do there. And the next one, I'm working with cosine inverse of -1. I know that my inverse cosine has exists in quadrant 1 and 2, so I'm going to be over here on the left all the way around. That's going to exist at pi. Nothing else for me to do there. I know for my sine inverse, I'm going to have a triangle in either quadrant 1 or 4. In this case, I have a negative sign, so I know that I am in quadrant 4. So I know that my values are going to be for the 45-degree triangle. So I know that that's going to be negative pi over 4. Okay? It is not going to be 7 pi over 4. 7 pi over 4 is not in the domain for the inverse function. Let's move on over to this section. I have tangent inverse of root 3. So I know that tangent is going to exist in quadrant 1 or 4. It's positive, which tells me I am going to be in quadrant 1. Sorry, I keep wanting to draw a triangle and I don't like the way it looks. Okay, so that's going to be root 3 over 1, which tells me I'm working with a pi over 3 triangle. And so the solution to this is pi over 3. Now I'm working with sine inverse. I again know that this exists in 1 or 4. In this case, sine is negative, so I know that it's going to exist in quadrant 4. My opposite side is negative root 3. Hypotenuse is 2, so adjacent is 1. Okay, that means I'm working with negative pi over 3. Again, this is not the positive angle because the domain is negative pi over 2 to pi over 2. Okay, that is an important distinction for us. For f, I'm working with cosine inverse of 0. I know that this is the spot where I'm going to reach cosine of 0. That's going to be at pi over 2. Okay, the last 5 have both. So what you're going to do is work from the inside out. So I'll go ahead and use 2 different colors. I'll go ahead and do green for the inside. So for the inside, I know that cosine inverse exists in quadrant 1 or 2. In this case, it is going to be quadrant 1 because I know that it's negative. So then here is my triangle. I recognize that that is going to be 2 pi over 3. Okay, so that's going to be 2 pi over 3. And so now what I'm doing is I'm going to go ahead and take tangent, okay, tangent of that 2 pi over 3. Tangent of 2 pi over 3 is going to be negative root 3, which is going to be my final answer. Okay? Let's repeat that process for h. So I'm going to find cosine of 0. Again, I know where that's going to be. That's going to be at pi over 2. So here we have pi over 2. Okay, and now I want sine inverse of pi over 2. Okay, so pi over 2 sine inverse, I know that the value of that is just going to be, there it is just going to be a 1. Okay, I do know that that is not going to change. Okay, then I have tangent inverse of tangent of 5 pi over 6. So I'll go ahead and draw 5 pi over 6. Okay, again, this is just the regular one. So here we have 5 pi over 6. That's 1, negative root 3, and 2. Okay. I know that tangent is going to be negative 1 over root 3. And then I want tangent inverse of that. Okay. If tangent is negative, that forces me into quadrant 4. Okay, which means that the triangle that I'm now working with is negative pi over 6. Okay, because that is in our domain. That is where my tangent is going to be negative 1 over root 3. We have 2 more. So for this one, you are going to go ahead and draw a triangle. This is not one of the special triangles. If we want 4/5, that's going to be positive. So I have 4, 5. This is a 3, 4, 5 triangle. I just know that. I've worked with these before. So I know that cosine is going to be 4/5 for this guy. And then my regular sine value, so we're essentially saying sine of this triangle now, because we don't have the angle measurement, is going to be 3/5. Okay, because that would be opposite and hypotenuse. Finally, we're going to do something similar with this last one. We have arctan, so that's inverse of tangent. It's negative, so I'm going to go ahead and draw my triangle in quadrant 4. So opposite, adjacent. I do need to go ahead and find my hypotenuse. That's going to be square root of 13. 2 squared plus negative 3 squared equals r squared, and that will lead to root 13. That is the triangle I'm working with. Okay, so then again, similar to before, what I'm really saying is I want the cosine value of this triangle, which is going to be adjacent over hypotenuse. So we're going to have 2 over the square root of 13. Okay, all of these are just practice problems. Okay, I encourage you to go through these in the homework slowly, taking your time. Start working from the inside out.